Welcome to the Power Electronics class. Myself B. Veernarayana, Senior Assistant Professor, Department of Electrical and Electronics Engineering. We are completing the first unit till now. Coming to the second unit, AC to DC converters, which is called rectifiers. Coming to the course, unit 2 outcomes. At the end of this unit, student will be able to classify and explain the operation of single phase controlled converters. Coming to the unit outcome 2, classify and explain the operation of 3-phase controlled converters and explain the effect of source inductance on single phase controlled converters and 3-phase controlled converters. Coming to the contents of this second unit, AC to DC single phase converters. In this, we are going to study about the single phase half wave controlled rectifiers with different types of the loads like R load, RL load and RLE loads, and single phase full wave controlled converters. In this, we are going to discuss about center tapped and bridge configurations for different types of the loads, R load, RL load and RLE loads, RL load without freewheeling diode and with the freewheeling diode in continuous conduction mode, and later we concentrate on single phase semi converter with R load and RL load with the freewheeling diode and effect of source inductance in single phase bridge rectifier with continuous conduction, and we will look at some problems. This is the first half of the second unit, AC to DC single phase converters, and second half AC to DC 3-phase converters. AC to DC 3-phase converters. In this 3-phase half wave controlled rectifier with R load and RL load, 3-phase fully controlled rectifier with R load, RL load and RLE load, and 3-phase semi controlled converter with R load, RL load and effect of source inductance on 3-phase controlled converter and problems. So coming to the first module, classification of controlled converters and single phase half wave controlled converter. At the end of this class, the learning outcome, the student will be able to, first learning outcome 1, classify the controlled converters. Learning outcome 2, explain the operation of single phase half wave controlled converter with R load and RL load. So what is the rectifier means? Simply the rectifier is the power electronic converter which is used to convert AC to DC. If you have the AC source, if you want to convert the AC source into the DC, then you go through the rectifier. So we have different types of the rectifiers, depends on the output voltage. If you have the fixed DC output voltage from the fixed AC input voltage, that is called uncontrolled rectifier. And if you have the variable DC output voltage from the fixed AC input voltage, that is called controlled rectifier. So generally in our power electronics language, converter means one form of energy into another form. If you use power electronic converter to convert one form of energy into another form, that is simply called the converter, like rectifier which converts AC to DC, one converter, chopper DC to DC converter, inverter which converts DC to AC converter. But in power electronics language, we will, for sake of simplicity, universally we term as converter is simply considered as the rectifier. Converter is simply considered as the rectifier. So you don't confuse. In this first unit we will call sometimes phase controlled converter or phase controlled rectifier, both are same. Converter is simply consisting in power electronics language rectifier. Okay, so answer sometimes we term it as single phase half wave converter. Converter is nothing but rectifier, you consider like that. So coming to this, rectifier is a circuit which converts the AC supply into the DC supply. Depends on the output voltage, the converters or rectifiers are classified into two types. Those are controlled rectifiers and uncontrolled rectifiers. If you go through the controlled rectifiers, controlled, the name itself, controlled, that means we are able to control the output voltage. Then if you convert the fixed AC to variable DC, that is called controlled converter or controlled rectifier. And if you convert this fixed AC into fixed DC, then that is called uncontrolled rectifier. That means the output voltage should be constant. So these are the two different types of the converters. And before inventing the power semiconductor devices, if you want to DC supply, simply we go through the motor generator set. After inventing the power semiconductor devices, that motor generator set simply replaced by the power semiconductor devices. By using these power semiconductor devices, we will design the converter which converts the AC supply into the DC supply. And coming to the applications of this DC source, those are used in steel rolling mills, paper mills, printing presses and textile mills, and traction systems working on DC, and similarly portable hand tool drives or high voltage DC transmission, or if you go through the battery operating conditions, if you simple example, if you go through the mobile phone to charge the battery, simply we require the DC source. So simply we will go through these rectifiers which converts the AC supply into the DC supply. And coming to the classification of the rectifiers, so mainly the rectifiers are classified depends on the output level. Those are classified as either controlled rectifier or uncontrolled rectifier. We already said if you go through the uncontrolled rectifier, the fixed AC is converted into the fixed DC. If you go through the controlled rectifier, here fixed AC is converted into variable DC. And coming to the based on AC supply, the controlled converters or uncontrolled converters together classified into two types, like single phase rectifiers and three phase rectifiers. So we have different types of the sources, like if you go through the AC source, we have two types of the AC source, either single phase AC supply or three phase AC supply. Then depends upon the supply, these controlled converters or rectifiers are classified into two types, like single phase rectifiers and the three phase rectifiers. And based on output voltage, we already said both the single phase rectifiers and the three phase rectifiers further classified into two types, like uncontrolled rectifiers and controlled rectifiers. Uncontrolled rectifiers and controlled rectifiers. And again, these uncontrolled rectifiers and controlled rectifiers based on output pulses, number of pulses present in the output voltage, both these uncontrolled rectifiers and controlled rectifiers together classified into two types, like half wave rectifiers and full wave rectifier. Half wave rectifier and full wave rectifier. Again, the full wave rectifier is classified into two types based on circuit configuration or circuit arrangement. Those are midpoint type converters or midpoint type rectifier and bridge type rectifier. Midpoint type rectifier and bridge type rectifier. Based on quadrant operation, again this bridge type rectifier is further classified into two types, like fully controlled converters or semi converters. Fully controlled converters or semi converters, these are also called as the half controlled converters. Half controlled converters. Similarly, the three phase rectifiers are also classified as three phase half wave rectifiers and three phase full wave rectifiers. Again, three phase full wave rectifiers are classified into center tap bridge type rectifiers and bridge type rectifiers. Again, those bridge type rectifiers are classified into three phase fully controlled converters and three phase semi converters. We will discuss each and every classification of these rectifiers. So basically here, if you go through these uncontrolled rectifiers and controlled rectifiers, uncontrolled rectifiers means we are getting fixed DC output voltage from fixed AC input voltage. So these converters are designed by using the uncontrollable devices like diodes. If you go through these controlled rectifiers, we are getting the variable DC from the fixed AC input voltage, then these controlled rectifiers can be designed by using the controllable devices like SCRs or thyristors. So this is the basic difference. We will discuss the controlled converters. So first classification, simply we go through this single phase half wave controlled converter with R load. In our syllabus we have controlled converters. We already discussed that uncontrolled converters like diode, rectifier circuits you already studied in the pulse and digital circuits which are covered in the past semesters. Hence why we concentrate only on the controlled converters. So in controlled converters, first we go through the single phase controlled converters. Again we will classify the single phase controlled converters are classified again into half wave controlled converters and full wave controlled converters. First we go through the single phase half wave controlled converter with R load. So coming to this is a circuit diagram representation of single phase half wave controlled converter with R load. It consisting source, which is the AC, and it is the resistive load. I just want to transmit this AC source to the resistive load through the SCR, controllable switch. So this is a simple representation of single phase half wave controlled converter. It consisting source, SCR, resistive load. Here V0 is the output voltage across the resistor and I0 is the current flow through the load. So coming to this operation, here I am taking this single phase AC supply which is considered as Vs is equals to Vm sin omega t is taken as the source, this one magnitude. Here Vm is the maximum voltage. Vm is the maximum voltage. So coming to the operation, during the positive half cycle of the supply from 0 to pi, here this terminal A and this is taken as B and this is C and this is the D, for example. So during the positive half cycle of the supply, terminal A is positive and B is negative. Corresponding that, here this is the anode, it is the cathode and it is the gate. So you already know when anode is made positive with respect to the cathode, then the SCR comes to the forward biasing mode. Forward biasing mode. And at omega t is equal to alpha, at this instant we provide the gate pulse to the SCR. So from alpha to pi, the SCR comes to the on state. From 0 to pi, SCR will be in the forward biasing mode. The forward biasing mode is also considered as the off state of the SCR. And at omega t is equal to alpha, at this instant we provide the gate pulse to the SCR. Then from alpha onwards the SCR comes to the on state. Here alpha is called the firing angle. Alpha is called the firing angle. So how can you define the firing angle? Means the angle at which the instant SCR comes to the on state is called firing angle. The angle at which the instant SCR comes to the on state is called firing angle. So here we take at this instant we consider as the alpha. Here for sake of simplicity in the circuit we did not represent the firing circuits. We have different types of the firing circuits, R firing circuit, RC firing circuit, UJT firing circuit. Out of these the UJT firing circuit is used to provide the instantaneous pulses to trigger the SCR. Instantaneous pulses means at which the instant if you want to turn on the SCR, for that SCR we are able to provide the firing pulses or gate pulses which are available across gate and cathode terminals of the SCR. So here at omega t is equal to alpha, we provide the gate pulse to the SCR. So from alpha onwards it comes to the on state. So from alpha to pi, here from alpha to pi, this portion of the source voltage is transmitted to the load, and the current flow through the circuit is A plus, thyristor, resistive load and B minus. In this way the current flow through the circuit, and whatever the voltage is available is transmitted to the load. So simply from alpha to pi, the output voltage follows the source voltage. So this part of the source is available across the load. Here SCR will be in the on state. Hence why this Vm sin alpha is available across the load. And coming to the current waveform, here we have the purely resistive load na. So the current is always in phase with respect to the voltage. So the current waveform is similar to the output voltage waveform. Here the magnitude should be depends on Vm by R. If you take R is equal to 1, then both output voltage and output current will have the same magnitude. If you have the high value of the R, then the current magnitude should be decreased. Depends on the value of the resistance, the magnitude should be changed, but the phase of the output current is in phase to the voltage. And see here, from 0 to alpha, what is the state of SCR? The SCR will be in the forward biasing mode. Forward biasing mode means off state. When the SCR will be in the off state, the source voltage will be available across the SCR. Hence why this small portion from 0 to alpha is available across the SCR, this portion. And from alpha to pi, what is the state of SCR? SCR will be in the on state. So if your SCR will be in the on state, the total source voltage is transmitted to the resistive load through the SCR. Hence why we are assuming ideal SCR. Hence why there is no voltage drop across the thyristor. There is no voltage drop across the thyristor. That means the voltage across the thyristor during the on state of the SCR is 0. And we have some output voltage and output current. And at omega t is equal to pi, the output voltage is 0 and output current is also 0. And from pi to 2 pi, during the negative half cycle of the supply, what happens here? During the negative half cycle of the supply, terminal A, B, C, D, terminal A is negative and B is positive. During the negative half cycle of the supply, terminal A is negative and B is positive. Corresponding that, here anode is made negative and cathode is positive, then the SCR will be in the reverse biasing mode. So reverse biasing mode means from pi to 2 pi, the SCR will be in the off state. At omega t is equal to pi, output voltage 0 and output current is 0. After the pi, the negative voltage is available across the SCR, so SCR goes to the off state. That phenomena of the off state of the SCR is simply called the line commutation or class F commutation or natural commutation. Natural commutation means here we did not use any external circuits to turn off the SCR. Simply depends upon the source. Whenever the source goes to the negative half cycle, automatically the SCR goes to the off state. That is simply called the natural commutation. And from pi to 2 pi, the SCR will be in the off state, that is in reverse biasing mode. So if it is in the reverse biasing mode, what happens? The total source voltage is available across the switch. So what is the available source voltage? This negative half cycle. So from pi to 2 pi, the total negative half cycle will be available across the switch. That means across the SCR. Hence why the output voltage is 0 and output current is also 0 from pi to 2 pi. Again from 2 pi to 3 pi, again we have the positive half cycle of the source. Again the SCR comes to the forward biasing mode. At omega t is equal to 2 pi plus alpha. We provide the gate pulse to the SCR. So from 2 pi plus alpha to 3 pi, again the SCR will be in the on state, and the portion of the source voltage from 2 pi plus alpha to 3 pi is transmitted to the load. Hence why 2 pi plus alpha to 3 pi we have some output voltage, and out 2 pi plus alpha to 3 pi we have the output current. From 2 pi to 2 pi plus alpha, what is the state of SCR? It is in forward bias, hence why off state. We have some voltage across the SCR. 2 pi plus alpha to 3 pi, on state of the SCR, there is no voltage, hence why 0. And 3 pi to 4 pi, again negative half cycle of the supply. SCR will be in the reverse biasing mode. It is in off state. Simply, if the SCR is in off state, source voltage is available across the SCR. Output voltage and output currents are 0. If the SCR is in the on state, source voltage is transmitted to the load. We have some output voltage and output current. We already said in the first class, all the power semiconductor devices acts like switches. If the SCR is on, there is no voltage across the SCR, you have some output voltage and output current. If the SCR is off, source voltage is available across the SCR, and output voltage and output currents are 0. So this is the simple representation of output voltage and output current and voltage across the thyristor. And coming to the average DC output voltage, should be find out like here average DC output voltage V0 is equals to how many pulses you have generated in the output voltage waveform for completion of one full cycle. Here this is the total time period. For completion of one full cycle in the output voltage waveform we have single pulse. So we will consider as V0 is equals to 1 by 2 pi. Here 1 represents the number of pulses in the output voltage waveform, and 2 pi is the total time period. 1 by 2 pi integral, what is the duration of the pulse here? Duration of the pulse means from alpha to pi we are getting the output voltage waveform. So we will write here alpha to pi, how much voltage you transmitted to the load? Source voltage. What is the source voltage here? Vm sin omega t d omega t. So the average DC output voltage simply given by V0 is equals to 1 by 2 pi integral alpha to pi Vm sin omega t d omega t. So by simplifying this expression, what you will get? Take Vm common, Vm by 2 pi integral sin omega t minus cos omega t, and you replace the limits between alpha to pi. So what you are getting here? So Vm by 2 pi minus cos pi minus of minus plus cos alpha. So finally you are getting Vm by 2 pi into cos 180 is minus 1 minus of minus plus 1. So nothing but 1 plus cos alpha. This is the average DC output voltage of single phase half wave controlled converter with R load. The average DC output voltage is given by V0 is equals to Vm by 2 pi into 1 plus cos alpha. And similarly, if you want to find out the average output current, I0 is equals to V0 by R, which is nothing but Vm by 2 pi R into 1 plus cos alpha. Here we are getting Vm by 2 pi. If you want to I0 na, Vm by 2 pi R into 1 plus cos alpha. That is the average DC output voltage. And if you go through the RMS output voltage, Vrms is equals to 1 by 2 pi. Why we will take 1? For the completion of the one complete cycle, we are getting only single pulse in the output voltage waveform. So 1 by 2 pi integral alpha to pi Vm square sin square omega t d omega t whole power 1 by 2. This is the formula for RMS output voltage. So by simplifying this expression, what you will get, take Vm square out of the whole power 1 by 2. So Vm into 1 by 2 pi integral alpha to pi. This sin square omega t is written as 1 minus cos 2 omega t by 2 d omega t whole power 1 by 2. So here by simplifying this expression, you are getting Vm into, so 1 by 4 pi, and apply the integration, integral 1 into d omega t, that is omega t between the limits alpha to pi, minus integral cos 2 omega t, it is sin 2 omega t by 2 between the limits alpha to pi whole power 1 by 2. By simplifying this expression, what you are getting here, Vm into pi minus alpha by 4 pi minus sin 2 pi 0 minus half minus sin 2 alpha. What you are getting finally, sin 2 alpha by 8 pi whole power 1 by 2. So finally by simplifying that expression, we are getting Vrms is equals to, see, Vrms is equals to, take Vm out of the root, you brought 2 root pi, what you are getting here, pi minus alpha plus sin 2 alpha by 2 whole power 1 by 2. That is the RMS output voltage. So here see here, Vrms is equals to Vm by 2 root pi minus alpha plus sin 2 alpha by 2 whole power 1 by 2. This is the RMS output voltage wave expression, and this V naught is the Vm by 2 pi into 1 plus cos alpha. And RMS load current IRMS is nothing but Vrms by R. And if you want to find out the power delivered to the resistive load, then we are getting the formula RMS load voltage into RMS load current, which is given by either Vrms into IRMS or V square RMS by R or I square RMS into R. And input volt ampere is given by RMS voltage source into total RMS line current. So what you are getting here, Vs into IRMS. These are very, very important formulas to solve the problems in control converters. And input power factor, very, very important. Input power factor is given by power delivered to the load divided by the input volt ampere. Power delivered to the load nothing but Vrms into IRMS divided by input volt ampere, which is Vs into IRMS. So by substitute these here, we are getting Vrms divided by Vs. The final expression here, the input power factor is equals to 1 by root 2 pi into pi minus alpha plus sin 2 alpha by 2 whole power 1 by 2. And circuit turn off time, very, very important formula. Circuit turn off time is simply given by the pi by omega seconds. Circuit turn off time should simply find out, depends on the half time of the SCR. How much time half time here? Simply observe here. If we go through the half time from pi to 2 pi, the SCR will be in the off state, that is in the reverse biasing mode. Then the circuit turn off time is simply given by pi by omega seconds. Pi by omega seconds. And here the average DC output voltage is Vm by 2 pi into 1 plus cos alpha. So if you go through this, V naught is equals to Vm by 2 pi into 1 plus cos alpha. So here if alpha is 0, what you are getting V naught? V naught is equals to Vm by 2 pi into 1 plus cos 0, 1. So finally you are getting V naught is equals to Vm by pi. That is the maximum output voltage. And if alpha is equals to 180, then V naught is equals to Vm by 2 pi into 1 plus cos 180. What is cos 180? Minus 1. Minus 1 plus 1, 0. So finally V naught is equals to 0. So if alpha is 0, we are getting the maximum output voltage, which is Vm by pi. If alpha is equal to 180, then the output voltage is 0. That means if you provide the firing angle is low, then the conduction angle is high and you are getting the maximum output voltage. If you increase the firing angle, corresponding that the conduction angle decreases and corresponding the output voltage also decreases. So we are able to the output voltage from 0 to Vm by pi by varying the firing angle from pi to 0. If the firing angle is 0, then we are getting the maximum output voltage, which is Vm by pi. If the firing angle is 180, then the output voltage is 0. So by varying this firing angle, we are able to control the output voltage, hence why it is named as controlled converter. Hence why it is named as controlled converter. So this is a simple representation of single phase half wave controlled converter with R load. So coming to the next one, single phase half wave controlled converter with RL load. Single phase half wave controlled converter with RL load. Previously we discussing single phase half wave controlled converter with R load. So coming to this single phase half wave controlled converter with RL load, the circuit consisting source, which is Vs is equals to Vm sin omega t, SCR, and here the load can be changed to RL. The combination of series resistance and the inductive elements are connected as the load to this half wave controlled converter. That is a simple representation of single phase half wave controlled converter with RL load. So what happens if you keep this inductor in the load side? So coming to this operation, here we have the source voltage, Vs is equals to Vm sin omega t. So I am considering the source again here, and it has the maximum voltage like Vm at omega t is equal to 90 degrees. And if you go through the terminals here, A, B, C and D. So coming to the operation of this half wave controlled converter with the RL load, during the positive half cycle of the supply, same, terminal A is positive and B is negative, corresponding that SCR will be in the forward biasing mode. If the SCR is in forward biasing mode, means that is in the off state of the SCR. At omega t is equal to alpha, we provide the gate pulse. So consider this gate pulse representation here, and at omega t is equals to alpha, here we provide the gate pulse. So up to alpha, what is the state of SCR? SCR will be in the forward biasing mode. Forward biasing mode means there is no output voltage and there is no output current. Simply the source voltage is available across the thyristor. The source voltage is available across the thyristor from 0 to alpha. At omega t is equal to alpha, we provide the gate pulse to the thyristor. Then SCR comes to the on state. Once the SCR comes to the on state, the source voltage is transmitted to the load and the output voltage simply follows the source voltage. So this portion from alpha to pi, this portion of the source voltage is available across the load. Hence why from alpha to pi simply we follows the source voltage. And due to the presence of the inductor in the load side, it does not allow the sudden change of current. So the current flow through the circuit, whenever the SCR comes to the on state, the current flow through the circuit is through the SCR R, L, B minus. The current flow through the circuit is A plus, thyristor, resistive load, R, L, B minus and A plus. In this way, from alpha to pi, due to the presence of the inductor, it stores the energy as in the form of electromagnetic field. So slowly the current flow through the inductor or the current flow through the load is increases. If you go through the previous, we have resistive load now, then the current is in phase with the voltage. But if you go through the inductive element, if the reactance offered by the inductive dominates the resistive load, then we have the inductive effect on the load side. Then due to the presence of the inductor, the current lags to the voltage by an angle phi, depends on the value of the inductor. So the current, some energy must be stored in the inductor from alpha to pi. Hence why, observe here, at omega t is equal to pi, even though the output voltage is 0, the output current cannot be 0. The output current cannot be 0. And due to the energy stores in the inductor from alpha to pi, actually after pi the reverse or the negative voltage is available across the SCR. Even though the negative voltage is available across the SCR, that SCR does not comes to the off state. We clearly said, if the SCR comes to the off state, you maintain two conditions. What are those? First, you must ensure that the current flow through the SCR is below the holding current or 0. And second one, the negative voltage is available across the SCR. Even though the negative voltage is available across the SCR from pi to 2 pi, the SCR does not comes to the on state. So the conduction portion of the SCR is extended up to the certain instant that depends upon the inductor. So at omega t is equal to pi, even though the output voltage 0, the output current cannot be 0. So the energy stores in the inductor is discharges from pi to some an extent which is called beta, that is called extinction angle. So that extinction angle should depends upon the value of the inductor. If you have the large value of the inductor, then it will take large time, hence why this extinction angle is high. If you have the low value of the inductor, within short period of time, the energy stores in the inductor is discharges to the source, then the extinction angle is low. So this extinction angle should depends upon the value of inductor, and from pi to beta, the energy stores in the inductor is discharges from inductor to the source through the same thyristor. Hence why the conduction portion of the SCR is extended up to beta. So the source voltage is transmitted to the load up to beta. Hence why this negative portion of the source voltage is available across the load. So here the positive portion simply represents some energy is transmitted from source to the load, and the negative portion of the output voltage means some energy is transmitted from load to source. So due to the presence of the inductor, as long as alpha to pi thyristor will be in the on state, some energy must be stored in the inductor. At pi, even though the negative half cycle will be available across the SCR, it does not comes to the off state. Why? Because there was some energy must be stored in the inductor, hence why that energy stores in the inductor is completely discharges, then the SCR comes to the off state. Hence why, due to the presence of the inductor, the conduction portion of the SCR is extended up to the instant where the energy stores in the inductor is completely discharges. That indicates by the beta, extinction angle. So the conduction portion of the SCR is extended up to the beta. So from alpha to beta, the SCR will be in the on state, that should be represented by the gamma. Here gamma is the conduction angle and it is the firing angle, and this beta is measured from the reference. So finally alpha plus gamma is equals to beta. The relation between these three, here alpha is the firing angle, gamma is the conduction angle, and beta is the extinction angle. So up to beta, the SCR will be in the on state. So blindly from alpha to beta, you follow the source voltage as the output voltage. In this output voltage waveform, this positive portion represents some energy is transmitted from source to the load, and this negative portion represents some energy is transmitted from load to the source. So up to beta, SCR will be in the on state, hence why there is no voltage across the SCR. There is no voltage across the SCR. And from beta to 2 pi, the negative voltage at the negative half cycle is available across the SCR. Then the SCR is automatically comes to the off state. So from beta to 2 pi, this portion of the source voltage is available across the SCR. And beta to 2 pi, SCR will be in the off state. Hence why there is no voltage and there is no current. Again from 2 pi to 3 pi, again SCR will be in the forward bias. Again at 2 pi plus alpha, again here we provide the gate pulse to the SCR. So from 2 pi plus alpha to 3 pi, you have the output voltage, and there was some energy must be stored in the inductor, and the energy stored in the inductor is discharges here. So up to the instant you have the negative output voltage, small peak of the negative voltage, again off state. You can observe here when the SCR will be in the off, then output voltage is 0 and this total source voltage is available across the SCR. So this is a simple output voltage, output current and voltage across the thyristors during the on state and off state of the SCR. So what happens, you can observe here, if you have the RL load, it does not comes to the off state, SCR does not comes to the off state at omega t is equal to pi. So whenever the energy source in the inductor is discharges, then the SCR may goes to the off state. So due to the presence of the inductor, what you observe here, the conduction portion of the SCR is extended up to the instant where the energy source in the inductor is completely discharges. That portion is simply represented by the extinction angle. And coming to the output voltage expression here, in the output voltage waveform, for completion of one full cycle, here we are getting the single pulse, hence why we will write V0 is equals to 1 by 2 pi integral, limits are alpha to beta, you have the output voltage. So alpha to beta Vm sin omega t d omega t. By simplifying this expression, Vm sin omega t means minus cos omega t, you replace the limits, finally you are getting Vm by 2 pi into cos alpha minus cos beta. This is the output voltage expression. And RMS output voltage, simply Vrms is equal to same 1 by 2 pi integral alpha to beta Vm square sin square omega t d omega t whole power 1 by 2. So by simplifying this expression, finally you got Vm by 2 root pi beta minus alpha minus sin 2 beta minus sin 2 alpha by 2 whole power 1 by 2. And circuit turn off time, here circuit turn off time is the 2 pi minus beta by omega. We already said circuit turn off time should be find out, depends on the SCR is in the reverse biasing mode. What is the reverse biasing mode portion here? From beta to 2 pi. Then the circuit turn off time is given by 2 pi minus beta divided by the omega. That is the circuit turn off time of the SCR. That is simple single phase half wave rectifier with RL load. And next topic, single phase wave controlled converter with RL load and freewheeling diode. With RL load and freewheeling diode. So simply here again we have same source, single phase AC source, SCR, RL load, but in addition to this we keep the freewheeling diode. The freewheeling diode is always connected in parallel to the load. So here we have the RL load, so across this RL load we keep this freewheeling diode. So what happens if you keep the freewheeling diode under the RL load? What observations you can make here? Simply go through the explanation. Same here we have the during the positive half cycle of the supply. Simply this terminal is A, B, C and the D. Same during the positive half cycle of the supply, terminal A is positive and B is negative. Corresponding the thyristor is comes to the forward biasing mode. At omega t is equal to alpha, if you provide the gate pulse, then SCR comes to the on state. As long as the positive half cycle is present, this diode will be in the reverse biasing mode. And at omega t is equal to alpha, we provide the gate pulse to the SCR. From alpha to pi, SCR comes to the on state. If SCR is in the on state, then this source voltage is transmitted to the resistive inductive load through the SCR. Hence why the output voltage simply follows the source voltage. So this portion of the source from alpha to pi is transmitted to the load. And output current, so assume large value of the inductor and we go through the continuous conduction mode. So there was some energy must be stored in the inductor. Due to the presence of the inductor, from alpha to pi some energy must be stored in the inductor. And this is the current flow through the thyristor. As long as the thyristor will be in the on state, we have some output current, and this is the current flow through the freewheeling diode. If the SCR will be in the on state, then the freewheeling diode is in the off state. Hence why the current flow through the freewheeling diode is 0 and the voltage across the SCR is also 0 from alpha to pi. From 0 to alpha, SCR will be in the forward bias, hence why you have some source voltage across the SCR. Observe here, at omega t is equal to pi, even though the output voltage is 0, output current cannot be 0. Hence why, what happens here, at omega t is equal to pi, the energy stored in the inductor dominates the source voltage, then that energy stored in the inductor drives the freewheeling diode coming to the picture after pi. So from pi to 2 pi or 2 pi plus alpha, the energy stored in the inductor is discharges to the load through the freewheeling diode. If there is no freewheeling diode, then the energy stored in the inductor is discharges to the source through the SCR. If you keep the freewheeling diode, here what happens? The energy stored in the inductor is discharges through the freewheeling diode, and that energy stored in the inductor is transmitted to the load itself. So there is no current flow through the thyristor during the energy stored in the inductor. Hence why the current flow through the thyristor is bypasses or transmitted to the freewheeling diode. Hence why this freewheeling diode is also called the commutating diode, which is used to commutate the SCR. So if there is no freewheeling diode, the energy stored in the inductor is discharges to the source through the SCR, so SCR is continuously in the on state. If you keep the freewheeling diode, then major amount of the load current is discharges to the load through the freewheeling diode, then SCR is automatically goes to the off state. So observe here, when the SCR will be in the off state, this diode coming to the picture, it will act as the short circuit across the load, hence why the output voltage is 0 and current flow through the SCR will be 0. Then the current flow through the freewheeling diode will be discharging nature. So if we keep the large value of the inductor, then we are getting the continuous conduction mode, and the energy stored in the inductor is discharges continuously till the SCR comes to the on state. So from this pi to 2 pi plus alpha, the energy stored in the inductor is discharges through the freewheeling diode. Hence why the current will be discharges like this, and the current flow through the freewheeling diode is this one. And if the freewheeling diode is coming to the picture, then what is the state of SCR? Off state. If SCR will be in the off state, this negative portion of the source from pi to 2 pi plus alpha, that portion is available across the SCR. This is the voltage across the thyristor. And Again at 2 pi plus alpha we provide the gate pulse, again thyristor comes to the on state, again there was some energy must be stored in the inductor, again you have the current flow through the thyristor and current flow through the freewheeling diode is 0, voltage across the SCR is 0. Again at 2 pi plus alpha during the negative half cycle SCR is goes to the off state and the energy stores in the inductor is discharges through the freewheeling diode. So here see, here we have the current flow through the freewheeling diode and there is no current flow through the SCR. So these are the output voltage and output current voltage across the thyristors waveforms. What we observe, if you keep the freewheeling diode, there is no negative pulses in the output voltage. We are having only positive pulses. That means always the energy is transmitted from source to the load. There is no energy transmitted from load to the source. So the resultant power which delivers to the load is increases. If you go through the RL load without freewheeling diode, what you can observe here, from alpha to beta some power P1 should be transmitted from source to the load. From pi to beta the energy stores in the inductor is discharged to the source. So that power is taken as the P2. So the resultant power becomes P1 minus P2, which will be decrease. If you go through this RL load and the freewheeling diode, from alpha to pi some power should be transmitted from source to the load, and from pi to 2 pi plus alpha the energy stores in the inductor is again discharges to the load through the freewheeling diode. Hence why the resultant power should be increases. So the power delivered to the load increases, the first effect due to the presence of the freewheeling diode, and second one we are getting the continuous current waveform. If you have the large value of the inductor, due to the presence of the freewheeling diode the load performance is better, then we are getting the continuous conduction if we have the large value of the inductor in the load. And third one, input power factor is improves. Why? Because we already said input power factor is nothing but power delivered to the load divided by the input volt ampere. If you improve the power delivered to the load, input power factor is also improves. So these are the main advantages of the freewheeling diode. First one is load performance is better. Second one, power delivered to the load increases and we are able to getting the continuous conduction mode. And most advantage of the freewheeling diode, input power factor is improved. Input power factor is improved. These are the advantages of the freewheeling diode. And if you go through the freewheeling diode, the average load voltage is given by V0 is equals to, we are getting the single pulse in the output voltage waveform. So V0 is equals to 1 by 2 pi integral alpha to pi, limitations are changed, alpha to pi Vm sin omega t, and finally you got Vm by 2 pi into 1 plus cos alpha. And circuit turn off time is simply given by Tc is equals to pi by omega seconds. So this is a single phase half wave controlled converter with RL load and freewheeling diode. So at the end of this lecture, student will be able to classify the controlled converters and explain the operation of single phase half wave controlled converters with R load, RL load and the freewheeling diode. Okay, thank you.